Imagine holding the entire history of the universe in your hands, compressed into a single year. This is the concept of the cosmic calendar, introduced and popularized by Carl Sagan, a way to visualize the vastness of cosmic time in a scale you can comprehend. In this calendar, the Big Bang, the origin of space, time, and all matter, occurs at the stroke of midnight on January 1st. From that moment, every second, every day, every month, represents millions or even hundreds of millions of years in actual cosmic history. You feel the enormity of time, the slow unfolding of processes that shape everything around you, from galaxies to stars, from planets to life itself. As you trace the passage of cosmic months, you notice that the first stars ignite in the dark expanse, around mid-January. These stars form from clouds of hydrogen and helium, fused under the force of gravity. Nuclear fusion begins in their cores, producing energy and light that spreads across the universe. The earliest galaxies take shape from collections of these stars, slowly clustering under the influence of gravity. Your mind registers the scale. Hundreds of millions of years compressed into days. Yet the processes themselves unfold exactly as physics dictates, with no rush, no pause, only the relentless progression of natural laws. By the end of February, the first heavier elements begin to appear, forged within stars. Elements like carbon, oxygen, and iron emerge from stellar cores through fusion. These atoms, expelled in supernovae, seed the surrounding space with the raw materials for planets and, eventually, for life. You follow this slow dispersal, understanding that every atom in your body has a lineage tracing back to these ancient stellar furnaces. The cosmic calendar shows you that the universe is not only ancient but generative, producing the very building blocks of life over billions of years. Moving into March and April, galaxies continue to assemble and interact. Gravity pulls clusters of stars together, forming more complex structures. You note how these early galaxies are observed through powerful telescopes, appearing as faint smudges of light billions of light years away. Their light has traveled for nearly the entire history of the universe to reach us, carrying information about conditions long before our sun existed. You recognize that looking outward in space is also looking backward in time. This dual perspective allows you to connect the abstract enormity of cosmic time with tangible observation, reinforcing the reality of the processes you are imagining. As the months progress toward September, your focus narrows to a small corner of the universe, our Milky Way galaxy. It forms from the merging of smaller galaxies, slowly building its spiral arms and dense central bulge. Stars are born in clouds of molecular hydrogen, and clusters of young stars move together through the galaxy. Gravity sculpts orbits, and over billions of years, the sun coalesces from a spinning disk of gas and dust. Planetary formation begins, including the assembly of Earth around 4.5 billion years ago. The cosmic calendar compresses these billions of years into a matter of days, yet each process remains bound by well-understood physics, from accretion to orbital dynamics. As you reach mid-December on this cosmic scale, Earth has formed, and life begins in the form of microscopic organisms. The first single-celled life appears late in the year, reminding you that for most of cosmic history, the universe exists without conscious observation. Geological processes, tectonic shifts, and chemical interactions create environments suitable for life to emerge. By imagining these early days, you perceive how slowly complexity accumulates, from simple molecules to living cells, all guided by chemistry and environmental conditions that can be measured, tested, and observed today. By December 31st, the last day of the cosmic calendar, all of recorded human history fits into the final minutes before midnight. Every civilization, every discovery, every individual life occupies a fraction of a second in comparison to the universe's age. You can feel the perspective shift as you realize the brevity of human time, yet also the remarkable acceleration of understanding. Science compresses centuries of observation and experimentation into tangible knowledge, revealing patterns and processes that stretch across eons. Every invention, every telescope, every observation contributes to our comprehension of time and space, connecting the brief span of human activity to the vast cosmic past. The cosmic calendar also allows you to track the major milestones with precise timing. The formation of multicellular life occurs in the early hours of December 17th, while the first dinosaurs appear around the evening of December 25th. Mammals rise on December 30th, and modern humans emerge only seconds before the year ends. These precise calibrations come from radiometric dating, fossil records, and astrophysical observations, each measurement reinforcing the reliability of this visualization. You appreciate that these numbers are not arbitrary. They are constructed from layers of evidence collected over decades, demonstrating both the immensity and the predictability of cosmic history. Throughout this visualization, you notice that time itself becomes more comprehensible. By assigning real durations to each calendar unit, the cosmic calendar transforms an abstract span of 13.8 billion years into a form your mind can intuitively grasp. You sense the continuity of natural processes, gravitational collapse, nuclear fusion, chemical evolution, and biological emergence. Each of these unfolds according to immutable laws, unbroken across time. The compression does not change the reality of these events. It simply situates them in a framework that aligns with human perception, helping you feel both the vastness of the universe and your own small, yet meaningful, role within it. As you dwell on the final seconds of this cosmic year, the timeline of human history becomes a delicate point at the edge of the universe's age. You reflect on the ways in which understanding the order and duration of events enhances clarity, curiosity, and humility. The cosmic calendar transforms abstract numbers into a living, measurable chronology, and through it, you sense the slow but continuous evolution of matter, energy, and life. This perspective sets the stage for contemplating the birth of stars, galaxies, and the very atoms that form every object around you, connecting you intimately with the unfolding of cosmic processes. You begin at the very start, where space, time, and energy emerge simultaneously. The Big Bang is not an explosion in space. It is the rapid expansion of space itself, carrying energy and matter along with it. Within the first fraction of a second, the universe undergoes extreme changes. Temperatures are unimaginably high, and energy dominates every process. Quantum fluctuations ripple through this early universe, tiny variations that will eventually determine the large-scale structures you observe billions of years later. These fluctuations are detectable today in the faint irregularities of the cosmic microwave background radiation, the afterglow of the Big Bang. As the universe expands, it cools. Within the first second, fundamental particles begin to form. Quarks, electrons, and neutrinos emerge from energy, following the rules of quantum mechanics and particle physics. Quarks combine into protons and neutrons, forming the nuclei of the simplest atoms. Neutrinos, nearly massless and interacting only weakly with other matter, stream through space almost unhindered, carrying information about these earliest moments. You follow the sequence carefully, noting that each transformation occurs according to well-established physical laws, measurable and consistent with laboratory experiments. After roughly 3 minutes, conditions allow for the fusion of protons and neutrons into light nuclei, primarily hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, determines the primordial composition of matter in the universe. The ratios of these elements are precisely measured today in distant gas clouds and in the oldest stars, confirming the predictions of theory. You feel the calm certainty of this process, knowing that the universe's composition is not random but a direct consequence of the physical conditions during its first minutes. For the next several 100,000 years, the universe remains a hot, dense plasma of nuclei, electrons, and photons. Light cannot travel freely because photons constantly scatter off charged particles. This era, sometimes called the photon epoch, is crucial in shaping the universe's evolution. You recognize that this state is directly observed through the cosmic microwave background, which provides a snapshot of the universe when it first became transparent. Around 380,000 years after the Big Bang, the temperature drops sufficiently for electrons to combine with nuclei, forming neutral atoms. Light can finally travel unimpeded, and the universe enters the era of recombination. The release of this ancient light allows you to observe the universe at a very young age. The cosmic microwave background appears as a nearly uniform radiation field, with minute variations corresponding to the density fluctuations from the earliest quantum processes. These fluctuations will guide the formation of galaxies, clusters, and superclusters. When you look at maps of this radiation, you see a direct imprint of the universe's infancy, an empirical record of events occurring long before stars or planets existed. You understand that even at this early stage, measurement and observation provide a clear window into the processes that shaped everything that follows. Over the next few 100 million years, gravity begins to gather matter into regions of slightly higher density. Hydrogen and helium coalesce into the first stars, marking the transition from the dark ages of the universe to the era of light. These population 3 stars are massive, short-lived, and responsible for producing the first heavier elements through nuclear fusion and supernovae. You follow the chain of events as the universe becomes increasingly structured, observing the gradual emergence of galaxies from clouds of primordial gas. These processes occur over timescales of hundreds of millions of years, yet each step is predictable according to the laws of gravity, thermodynamics, and nuclear physics. Observations with modern telescopes allow you to see galaxies as they appeared billions of years ago, effectively looking back in time. The light from these early structures confirms models of cosmic evolution, showing that galaxies form hierarchically, merging and growing into larger systems. The expansion of space itself continues, stretching light from distant galaxies and producing the cosmological redshift. This expansion is not a force pushing galaxies through space, but rather the growth of space between them, measurable by spectroscopy and precise astronomical surveys. You appreciate that each distant galaxy you observe represents a historical record, confirming that the sequence of cosmic events is both observable and consistent with theory. Throughout these early epochs, the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, guide every interaction. Gravity pulls matter together, forming stars and galaxies. Electromagnetism allows atoms to form and light to travel. The strong nuclear force binds atomic nuclei, while the weak force governs radioactive decay and certain fusion processes. These interactions are not hypothetical. They are measured, tested, and observed both on Earth and across the universe. You sense the order underlying the apparent vastness, a precise mathematical structure dictating every transformation, every reaction, and every collapse of matter into denser configurations. The timeline of the universe's first billion years sets the foundation for everything that follows. Light from the earliest stars illuminates the cosmos, ionizing surrounding hydrogen and ending the dark ages. Galaxies begin to cluster into larger structures, forming filaments and voids across the cosmic web. Each observation you consider, from spectroscopy to gravitational lensing, provides evidence that the universe evolves predictably from its hot, dense origin toward increasing complexity. Your mind traces the sequence carefully, following the gradual transition from a uniform plasma to a cosmos filled with luminous stars and forming galaxies. You also notice that time in this early universe behaves according to general relativity. The curvature of spacetime affects the propagation of light, the paths of matter, and the expansion rate itself. Observations of distant supernovae, the cosmic microwave background, and galaxy distributions allow precise measurements of the universe's age and expansion history. The combination of relativity and particle physics explains phenomena from the earliest seconds to the first billion years, creating a continuous, measurable timeline grounded in observation and theory. As you dwell on the universe's birth, you recognize that every element, every photon, and every particle traces its origin to these first moments. The energy and matter that eventually form stars, planets, and even life itself were present from the beginning, shaped and organized by physical laws. The expansion continues, the cosmic web grows, and galaxies evolve, all in accordance with the initial conditions set by the Big Bang. By understanding the earliest stages, you gain a perspective on both the scale of time and the predictability of natural processes, preparing your mind to observe the slow but inexorable formation of stars and galaxies that follows in the universe's unfolding history. You begin by observing vast clouds of gas and dust scattered across the expanding universe. These molecular clouds are primarily hydrogen and helium, remnants of the primordial nucleosynthesis that occurred in the first minutes after the Big Bang. Tiny variations in density, the result of quantum fluctuations from the earliest moments, provide seeds for gravitational collapse. Where density is slightly higher, gravity gradually draws material inward, and over millions of years, regions of gas condense into dense cores. These cores are the birthplaces of stars. Within each dense core, the balance between gravity pulling matter inward and gas pressure resisting collapse determines the formation process. As the material contracts, it heats up, converting gravitational potential energy into thermal energy. When the temperature and pressure at the core become high enough, nuclear fusion ignites. Hydrogen nuclei combine to form helium, releasing vast amounts of energy in the form of light and heat. You note that this ignition marks the creation of the universe's first true stars, called population 3 stars, which are massive and short-lived. Their intense radiation and rapid fusion cycles play a crucial role in shaping their surroundings. These early stars produce heavier elements through nuclear reactions in their cores. Elements like carbon, oxygen, and nitrogen, necessary for future planetary systems and life, are synthesized and dispersed into space when these stars explode as supernovae. You understand that every atom heavier than helium in the universe comes from these early stellar generations. Observing distant galaxies allows scientists to detect these processes indirectly, through spectral lines that reveal elemental composition, confirming that star formation enriches the cosmos over time. Clusters of stars begin to gather under mutual gravitational attraction, forming the first galaxies. These structures are not static. Gravity continues to pull them together, causing mergers and interactions. Over hundreds of millions of years, these proto-galaxies evolve into the spiral and elliptical galaxies observed in the modern universe. Their distribution is non-uniform, forming a cosmic web with dense filaments and vast voids. You notice that this large-scale structure is directly observable today through deep sky surveys, allowing you to connect theory with evidence. Inside galaxies, star formation continues in molecular clouds, regions dense enough for gravity to overcome internal pressure. Stars form in clusters, often in stellar nurseries observable in infrared and radio wavelengths. These nurseries provide direct evidence of ongoing formation processes, revealing how gas collapses, fragments, and ignites. You follow the physics carefully. As gravity concentrates matter, energy is released, angular momentum redistributes, and rotation shapes the resulting star systems. The process is slow on human timescales but constant and predictable across cosmic time. You also note the role of dark matter in galactic formation. Although invisible to telescopes, dark matter contributes most of the mass in galactic halos. Its gravitational influence governs the rate at which gas can collapse and stabilizes the formation of large-scale structures. Observations of galaxy rotation curves and gravitational lensing provide measurable evidence of dark matter's presence, linking its unseen effect to the observable distribution of stars. This interplay between visible and invisible matter guides your understanding of how galaxies assemble and evolve. As stars evolve, they follow well-understood life cycles determined by mass. Low-mass stars, like our Sun, burn steadily for billions of years, eventually forming white dwarfs. High-mass stars live shorter lives, producing supernovae that release energy and newly formed elements into interstellar space. These explosions trigger further star formation by compressing nearby clouds, creating a feedback loop that governs the growth and evolution of galaxies. You can observe remnants of these events in supernova remnants, nebulae, and enriched interstellar material, providing a continuous record of cosmic history. Observing galaxies at different distances allows you to see snapshots of their evolution. Light from distant galaxies takes billions of years to reach Earth, effectively allowing you to look back in time. By measuring redshift and spectral characteristics, scientists determine both distance and age. You recognize that this observational technique confirms the sequence of galaxy formation predicted by cosmological models, providing empirical grounding for theoretical frameworks. The interplay between observation and theory strengthens your understanding of how stars and galaxies emerge and evolve over hundreds of millions of years. The first supermassive black holes also begin to appear in the centers of some galaxies. Their formation is linked to the collapse of massive gas clouds and the merger of dense stellar remnants. These black holes influence star formation and galactic dynamics through their gravity and occasional energetic emissions. Quasars, observed as extremely luminous points in the distant universe, provide evidence of these early black holes accreting matter. You note that even the most extreme objects follow predictable physical principles, allowing measurement, modeling, and verification. Throughout this early era, cosmic expansion continues. Space stretches, carrying galaxies apart, while local gravity organizes matter into structures. Observations of the cosmic microwave background, galaxy distribution, and supernova distances quantify the rate of expansion and its change over time. You follow how general relativity and the cosmological constant govern these dynamics, providing a consistent framework that links the formation of stars and galaxies to the underlying expansion of space. This understanding transforms immense distances and timescales into measurable quantities. You notice that galaxies themselves are environments of ongoing chemical and dynamical processes. Stellar evolution produces heavier elements, gas clouds cool and collapse, and new generations of stars enrich the interstellar medium. Each step in this cycle is measurable through spectroscopy, elemental abundances, and kinematic studies. You appreciate that the universe builds complexity slowly, step by step, without any need for speculative mechanisms. Every observation confirms the continuous interaction of gravity, nuclear physics, and electromagnetic processes, creating the structures you now see across space. As you observe these processes, you begin to see the connection between distant galaxies and your own Milky Way. The same physical principles govern both, though local differences in mass, rotation, and history produce distinct structures. Spiral arms, central bulges, and globular clusters emerge naturally from the interaction of gas dynamics and gravity. Stellar populations vary according to age, mass, and composition, reflecting the cumulative history of star formation and chemical enrichment over billions of years. Each galaxy becomes a laboratory, allowing you to study universal laws in a diverse range of conditions. The gradual formation of stars and galaxies demonstrates the interplay of fundamental physics, observable evidence, and cosmic time. Gravity orchestrates large-scale structure, nuclear fusion powers individual stars, and radiation interacts with matter to shape the interstellar medium. You sense the rhythm of the universe unfolding. Slow, predictable, and measurable. Every galaxy you observe confirms the early conditions set by the Big Bang, the variations in density, and the subsequent gravitational collapse that produces luminous, structured systems. Through this understanding, you realize that the universe evolves systematically, producing stars, galaxies, and elements that will eventually seed planets. The processes you follow are observable today, whether in distant galaxies, stellar nurseries, or the remnants of supernovae. Each measurement reinforces the continuity of cosmic history, the reliability of physical laws, and the predictable unfolding of complexity. Your mind rests in the certainty that stars and galaxies emerge naturally, shaping the universe on scales both immense and intimately connected to the future formation of planetary systems. You watch as early galaxies light up the cosmos, their formation traced by gravity, nuclear physics, and observable evidence. The universe becomes increasingly structured, preparing the conditions for the birth of systems like our own, where stars cluster in stable orbits and planets can form. The expansion continues, matter continues to coalesce, and the cycle of creation and transformation carries forward, setting the stage for the emergence of our galaxy, our sun, and ultimately, the planets that surround it. You begin by observing the Milky Way, a spiral galaxy containing hundreds of billions of stars. Its formation began from smaller proto-galactic clouds, each influenced by gravity and dark matter. Over billions of years, these clouds merged, forming larger structures and producing regions of star formation. The galaxy's characteristic spiral arms emerge from the differential rotation of stars and gas, while a dense central bulge contains older stars with higher metallicity. You note that these structures are not random but the result of predictable gravitational dynamics, observed in other galaxies across the universe. In the halo surrounding the Milky Way, globular clusters orbit as dense collections of ancient stars. These clusters provide a record of the galaxy's earliest history. Stars within them are metal-poor, meaning they contain fewer elements heavier than helium. Observing their spectra allows you to determine their ages, confirming that some formed nearly as long ago as the galaxy itself. You recognize that these stellar populations act as natural timekeepers, preserving evidence of galactic assembly and chemical enrichment over billions of years. Within the galaxy's disk, interstellar gas and dust form molecular clouds, regions dense enough for new stars to develop. You see the cycle of star formation continuing. Clouds collapse under gravity, protostars ignite, and stellar winds influence their surroundings. Star clusters form, evolve, and disperse, contributing to the chemical complexity of the galaxy. These processes are observable through infrared and radio astronomy, which allow you to peer through dust that would otherwise obscure your view. The Milky Way is thus a dynamic, evolving system, where structure and activity are measurable and predictable. Your attention shifts to the solar neighborhood, a region of the Milky Way located about 26,000 light-years from the galactic center. Within this area, stars like the Sun form from a molecular cloud roughly 4.5 billion years ago. Observations of young stellar clusters and star-forming regions reveal the physical mechanisms at work. Gravity compresses gas, angular momentum produces rotation, and magnetic fields influence the collapse and eventual ignition of nuclear fusion. Each step follows well-understood physical laws, consistent across the galaxy and in other galaxies as well. The Sun itself formed from a rotating disk of gas and dust, a solar nebula shaped by the balance of gravitational collapse and centrifugal forces. Tiny particles collided and stuck together, gradually building planetesimals, the precursors to planets. Meteoritic evidence confirms that these processes occurred over tens of millions of years, providing a precise timeline of early solar system formation. Isotopic ratios in meteorites allow you to date these events with remarkable accuracy, grounding your understanding in empirical measurement rather than speculation. Within the solar nebula, temperature variations influenced which elements and compounds condensed. Close to the protostar, refractory materials such as metals and silicates formed solid grains, eventually building terrestrial planets. Farther out, ices and gases accumulated to form gas giants. This distribution is predictable based on the physics of condensation, orbital dynamics, and accretion. Observing exoplanetary systems around other stars confirms that these patterns are common, demonstrating that the formation of planetary systems follows universal physical principles. As planetesimals collided and merged, larger bodies emerged, some massive enough to clear their orbits. This process, known as planetary accretion, produces stable planets with differentiated internal structures. The Earth, forming in the habitable zone, retained enough heat from accretion and radioactive decay to maintain a molten core, which generates a magnetic field through dynamo action. This field shields the planet from charged particles emitted by the Sun, a measurable effect that contributes to the long-term stability of the surface environment. The early solar system was also shaped by dynamic interactions. Giant planets migrated slightly from their original orbits, influencing the distribution of asteroids and comets. Some smaller bodies collided with early Earth, delivering water and organic compounds. Observations of other planetary systems suggest that such migrations and impacts are common, and isotopic analyses of Earth and meteorites confirm the timing and composition of these events. You see that planetary formation is not only predictable but also deeply interconnected with the evolution of the entire stellar system. Within the Milky Way, the Sun is one of many stars moving in a roughly circular orbit around the galactic center. Its velocity and position are measurable through proper motion studies and Doppler shifts. The gravitational influence of the galaxy's mass distribution, including dark matter, maintains the Sun's orbit. You observe that this movement occurs over hundreds of millions of years, yet the Sun remains within a relatively stable region, known as the galactic habitable zone. This stability is significant because it provides consistent radiation levels and minimal disruption, factors crucial for the long-term development of life on Earth. Studying nearby stars reveals the diversity of stellar properties in your region of the galaxy. Stars vary in mass, luminosity, temperature, and age, creating a local stellar environment rich in data. By comparing these stars, you understand the processes of stellar evolution, the frequency of star formation, and the distribution of elements necessary for planetary systems. Observational surveys, including spectroscopy and photometry, allow you to map the stellar population in detail, reinforcing a precise, evidence-based understanding of your neighborhood within the galaxy. The interstellar medium, composed of gas and dust, is continuously recycled. Material ejected from dying stars enriches the surrounding medium with heavy elements. Supernovae and stellar winds trigger new star formation, ensuring a constant renewal of galactic material. You perceive that the Milky Way is not static. It is an ongoing cycle of creation and transformation, observable through telescopes across multiple wavelengths. The combination of theory and observation confirms the predictability of these processes, governed by gravity, nuclear fusion, and the physical properties of matter. As you consider the Milky Way's structure, you notice its spiral arms traced by young, bright stars and star-forming regions. The disk, halo, and central bulge contain distinct stellar populations, each with characteristic ages and compositions. Observations of other spiral galaxies allow you to contextualize your findings, showing that the organization and evolution of galaxies follow consistent principles. You sense that the Milky Way, while unique in its detailed history, is a typical example of spiral galaxy dynamics and structure. The gradual assembly of your solar system within this galactic context highlights the interconnectedness of cosmic processes. Gravity, nuclear physics, orbital dynamics, and chemical evolution combine to produce stable planetary systems. Observations of meteoritic material, young stars, and distant galaxies confirm that these processes are ongoing throughout the universe. You understand that Earth's formation, its orbit, and its chemical composition are part of a much larger narrative, set against the backdrop of an evolving galaxy, where stars and planets form and interact according to measurable laws. You reflect on the precision of these observations. Every star, cloud, and planet follows predictable paths shaped by gravity and fundamental forces. The Milky Way itself is a laboratory, offering insight into the mechanisms that produced your sun and the planets that circle it. The processes you trace, from galactic assembly to planetary formation, prepare the environment for conditions that will eventually allow life to emerge, linking cosmic evolution directly to the origins of your world. You begin by observing the formation of Earth within the young solar system. Roughly 4.5 billion years ago, the planet forms through the process of accretion, as solid particles and planetesimals collide and stick together under gravity. The kinetic energy of these collisions generates intense heat, melting much of the material and producing a molten interior. Heavier elements, like iron and nickel, sink to form the core, while lighter silicates rise to form the mantle and crust. Radiometric dating of meteorites and terrestrial rocks allows precise measurement of these stages, confirming the timeline and processes of planetary formation. During these early stages, Earth is heavily bombarded by asteroids and comets, delivering additional material, including volatile compounds. Some impacts release sufficient energy to vaporize portions of the surface, while others may contribute water and organic molecules. Observational evidence from meteorite composition and isotopic ratios supports the theory that cometary and asteroidal material helped establish the planet's hydrosphere and chemical inventory. You notice that this delivery of water, combined with Earth's initial internal heat, establishes conditions capable of supporting long-term chemical reactions. As the molten surface cools, a primitive crust stabilizes, and the first oceans begin to form from condensed water vapor. Volcanic activity releases gases, producing a primordial atmosphere composed mainly of carbon dioxide, nitrogen, water vapor, and trace compounds. Oxygen is virtually absent at this stage, as no significant photosynthetic processes exist yet. This early environment, though harsh by modern standards, provides the chemical diversity and liquid water necessary for the earliest forms of life. Geological evidence in ancient rocks confirms the presence of water on Earth as far back as 4.3 billion years ago. Life appears in the form of single-celled microorganisms approximately 3.8 billion years ago. Fossilized microbial mats, known as stromatolites, provide direct evidence of these early organisms. Isotopic signatures in ancient rocks reveal metabolic activity, confirming that life was already capable of basic chemical energy conversion. These earliest life forms are simple, anaerobic, and microscopic, yet they represent a profound milestone: the emergence of self-replicating systems capable of evolution. You perceive that life begins not through sudden complexity, but through gradual chemical and biological processes bound by physics and chemistry. The first cells rely on chemical gradients and catalytic molecules to maintain homeostasis and reproduce. Nucleic acids, proteins, and lipid membranes assemble according to well-understood chemical principles, guided by the availability of elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Laboratory studies and observation of modern extremophiles, organisms that thrive in extreme environments, support models of early life, demonstrating that these processes are plausible under the environmental conditions present on early Earth. Over hundreds of millions of years, life evolves increasing complexity. Microbial ecosystems diversify, exploiting different energy sources, including chemical reactions in hydrothermal vents and photosynthesis, once light becomes accessible. Cyanobacteria, for example, develop oxygenic photosynthesis, gradually releasing oxygen into the oceans and eventually the atmosphere. Geological evidence, such as banded iron formations, records the timing of these changes, allowing you to trace the rise of oxygen and its impact on planetary chemistry. This slow accumulation of oxygen sets the stage for future aerobic organisms and more complex life. Tectonic activity shapes the surface environment during this period. Continents form through the collision and separation of crustal plates, creating shallow seas, volcanic regions, and mountain ranges. This dynamic geology influences the distribution of life and provides new niches for microbial ecosystems. Chemical weathering of rocks supplies minerals and nutrients to the oceans, supporting biological activity. Sedimentary deposits capture fossil evidence and chemical signatures, enabling precise reconstruction of early Earth environments. You notice that the interaction of geology and biology is measurable, predictable, and continuous. In the oceans, microbial mats and biofilms form layered structures, capturing sediment and minerals while contributing to chemical cycles. These formations provide the earliest fossil evidence of life, preserving structures that are billions of years old. Carbon isotope ratios reveal metabolic activity and energy processing by microorganisms, offering direct insight into the physiology of early life. Observations from modern microbial communities allow you to compare ancient and current processes, reinforcing the continuity of life's chemical and biological foundations. The development of metabolic pathways during this era illustrates the efficiency of natural chemical evolution. Autotrophic organisms extract energy from sunlight or chemical reactions, while heterotrophs exploit existing organic molecules. Enzymes and catalytic molecules accelerate reactions, increasing metabolic efficiency. You understand that these processes are governed by measurable chemical kinetics and thermodynamic principles, not by chance alone. Life expands and adapts within the boundaries set by physics, chemistry, and planetary conditions. By about 2.5 billion years ago, oxygen levels in the atmosphere begin to rise significantly in what is known as the Great Oxidation Event. This shift fundamentally changes planetary chemistry, allowing aerobic metabolism and paving the way for more complex life forms. Geological and isotopic evidence, such as oxidized minerals and sulfur isotope anomalies, precisely document this transition. You sense the interplay between life and planetary evolution, as biological activity actively modifies atmospheric and oceanic composition, a measurable and ongoing process in Earth's history. Throughout this period, evolution proceeds through gradual genetic changes, natural selection, and adaptation to environmental conditions. Fossil evidence, molecular biology, and comparative genomics provide a detailed, evidence-based framework for understanding how life diversifies. Complex multicellular organisms appear later, following billions of years of microbial evolution. Every stage is constrained by the physical and chemical environment, confirming that the progression from simple to more complex life is a continuous, observable process. You observe that the Earth, in its early billions of years, is simultaneously a chemical laboratory and a biological incubator. Volcanic activity, tectonics, oceans, and atmosphere interact with living organisms, establishing feedback loops that stabilize the planet's climate and chemistry. This dynamic system demonstrates the interconnectedness of life and planetary processes. Measurements of isotopes, fossil structures, and mineral composition provide precise evidence for these interactions, allowing you to trace the coevolution of Earth and its biosphere. Reflecting on the emergence of life, you realize that every molecule, every microbial cell, and every geochemical cycle follows predictable physical and chemical principles. Life arises not from randomness but from the cumulative effect of these processes acting over vast spans of time. The combination of water, energy, chemical diversity, and planetary stability creates the conditions for biological activity to flourish. You perceive that this foundation sets the stage for the gradual evolution of complexity, ultimately leading to multicellular organisms and the intricate biosphere that will eventually host humans. The history of Earth's formation and the emergence of life is recorded in rocks, isotopes, and fossils. Each observation confirms the predictability of planetary processes, chemical evolution, and biological adaptation. Through this evidence, you understand that life is both a consequence and a product of the physical universe. The gradual accumulation of complexity, driven by measurable laws of chemistry and physics, prepares the environment for future evolutionary innovations, establishing a link between planetary formation and the diversity of life that will eventually populate continents and oceans. You begin by observing the oceans, where life continues its slow, steady expansion. Microbial mats and biofilms dominate for billions of years, forming complex communities that cycle nutrients and influence chemistry. Cyanobacteria, producing oxygen through photosynthesis, gradually alter the atmosphere, setting the stage for aerobic organisms. Geological formations such as banded iron deposits record this change, allowing you to measure the pace of oxygen accumulation and its impact on Earth's surface environments. The long march of evolution is slow but continuous, recorded in stone and traceable through chemical signatures. Single-celled life begins to diversify, exploiting different energy sources. Some organisms metabolize sulfur, others fix nitrogen, and some continue using sunlight for energy. Each adaptation follows predictable biochemical pathways, demonstrating how life responds to environmental pressures. Genetic variation, arising through mutation and recombination, allows populations to adapt incrementally. You observe that this process does not occur uniformly. Local conditions create unique evolutionary trajectories, measurable through comparative genomics and fossil evidence. Evolution unfolds in accordance with natural laws, shaping life without need for external intervention. Approximately 600 million years ago, multicellular organisms emerge. These early metazoans, preserved in fossils such as the Ediacaran biota, show simple body structures, likely composed of specialized cells working together. The transition to multicellularity is guided by cellular communication, adhesion molecules, and genetic regulation, processes observable in modern organisms and supported by molecular biology. The evolution of multicellularity marks a critical milestone, creating the framework for specialized tissues and, eventually, organs, allowing more complex life forms to occupy diverse ecological niches. As life expands into shallow seas, the Cambrian explosion occurs roughly 540 million years ago. Fossil records reveal a rapid increase in morphological diversity and complexity, including the first evidence of hard shells, segmented bodies, and organized nervous systems. Evolutionary mechanisms, such as natural selection acting on heritable traits, explain the sudden appearance of these forms. You notice that the apparent rapidity is relative to geological timescales. Even this explosion spans tens of millions of years, each incremental change measurable through fossils, phylogenetic analysis, and comparative anatomy. Predation and ecological interactions drive further diversification. The development of eyes, appendages, and protective shells introduces new evolutionary pressures. Organisms adapt to exploit available resources, avoid threats, and occupy emerging habitats. Fossil evidence shows gradual modification of body plans, indicating that natural selection operates consistently across species and time. You observe that the dynamics of ecosystems, competition, cooperation, and niche differentiation create predictable patterns in the distribution and morphology of life, all verifiable through observation and measurement. During the Paleozoic era, plants colonized land approximately 470 million years ago. Vascular tissues allow efficient transport of water and nutrients, while structural support enables vertical growth. This terrestrial transition is evidenced in fossilized spores, stems, and leaves, allowing precise dating and reconstruction of early land ecosystems. Soil formation, nutrient cycling, and interactions with microbial communities support the establishment of complex terrestrial life. You notice that each adaptation follows physical and biological principles, demonstrating how life systematically exploits available environmental opportunities. Animal life follows plants onto land, with early arthropods and tetrapods emerging in response to new ecological niches. Fossil trackways, skeletal structures, and anatomical comparisons provide direct evidence of these transitions. Muscular, skeletal, and respiratory adaptations occur in step with environmental challenges, illustrating predictable responses to selective pressures. You perceive the continuity of evolution. Structures evolve incrementally, guided by functional necessity, environmental context, and heritable variation. Each adaptation is a response measurable through morphology, physiology, and paleontological data. The Carboniferous period demonstrates the impact of atmospheric oxygen on life. Elevated oxygen concentrations allow large body sizes in insects and amphibians. Fossilized remains and isotopic analysis confirm this relationship, demonstrating the connection between environmental conditions and evolutionary potential. You observe that physiology is constrained and enabled by planetary chemistry, creating a feedback loop between life and the environment. Evolutionary change is therefore not random but grounded in the laws of physics, chemistry, and biology. Mass extinctions periodically reset ecological landscapes. The end Permian extinction, around 252 million years ago, eliminates a majority of species, creating opportunities for surviving lineages to diversify. Evidence comes from abrupt changes in sediment composition, fossil abundance, and isotopic ratios. You notice that these events, though catastrophic, follow predictable patterns. Environmental stress, climate shifts, and geological activity shape the survival and subsequent adaptation of species. Evolution responds to external pressures in measurable, observable ways. After mass extinctions, new groups emerge, including early reptiles, mammals, and eventually dinosaurs. Fossil sequences allow precise reconstruction of lineage, morphology, and ecological role. Each transition is documented in skeletal evidence, trace fossils, and comparative anatomy. Genetic studies of living descendants provide additional confirmation of evolutionary relationships, creating a consistent and testable framework. You see that evolution is both gradual and episodic, predictable in its mechanisms but variable in its outcomes. During the Mesozoic era, life diversifies further in oceans, on land, and in the skies with the appearance of pterosaurs and birds. Observational evidence, including fossilized bones and feather imprints, confirms these developments. Environmental changes, such as continental drift and climate shifts, influence the direction and pace of evolution. Geological and paleontological data allow you to trace these interactions with precision, illustrating how life adapts predictably to shifting planetary conditions. By the Cenozoic era, mammals and birds dominate, and primates emerge approximately 60 million years ago. Fossil evidence of skeletal morphology, brain size, and dentition provides insight into ecological roles, diet, and behavior. Evolutionary pressures such as climate change, competition, and resource availability shape their diversification. Observations of modern primates, combined with paleontological data, reinforce the evidence-based understanding of lineage and adaptation. You follow the continuity from single-celled organisms to complex mammals, recognizing the consistent operation of evolutionary principles over vast timescales. You notice that throughout this long march, life is intricately linked to its environment. Geological processes, atmospheric composition, climate, and nutrient cycles all interact with biological systems. Observational evidence, both modern and fossilized, confirms that evolutionary change is measurable, incremental, and responsive to external conditions. The diversity of life emerges from a combination of heritable variation, selective pressures, and environmental context, producing the complexity you observe in both past and present ecosystems. The long march of evolution demonstrates the predictability of natural processes. Adaptation, diversification, and extinction all occur according to measurable principles of biology and chemistry. Fossil evidence, genetic analysis, and comparative anatomy provide multiple lines of confirmation, allowing precise reconstruction of life's history. You sense that every organism, ecosystem, and ecological interaction is part of a continuous, evidence-based process stretching from microscopic microbes to the mammals and primates that will eventually populate the planet. Reflecting on this gradual unfolding, you recognize that life's complexity arises slowly, predictably, and measurably. The cumulative effects of selection, adaptation, and environmental interaction produce a diversity that prepares the stage for humans and the intricate societies and technologies that will eventually observe, measure, and understand the cosmos. You begin by observing early hominins in Africa, approximately 6 million years ago. Fossil records indicate bipedal locomotion in species, such as Australopithecus, providing advantages in energy-efficient movement and environmental awareness. Skeletal structures show adaptations in the pelvis, lower limbs, and spine that support upright walking, allowing hands to manipulate objects. These anatomical changes are measurable and confirmable through comparative anatomy, demonstrating a gradual evolution toward the genus Homo. Around 2 million years ago, Homo habilis emerges, displaying larger brain volumes and the earliest known use of stone tools. Archaeological evidence reveals simple flake stones used to cut meat and process plant material. You observe that these tools are not random but designed to exploit physical properties of stone, illustrating early cognitive ability and problem-solving. Experimental archaeology confirms that similar techniques can reproduce these tools, reinforcing the evidence-based understanding of human technological development. Homo erectus appears roughly 1.8 million years ago, with further increases in brain size and body proportions closer to modern humans. Fossil evidence indicates the use of fire, as charred remains and hearth structures appear at multiple sites. Controlled fire enables cooking, warmth, and protection, influencing nutrition, social behavior, and survival. Anthropologists and archaeologists reconstruct these patterns through stratigraphy, radiometric dating, and contextual analysis, providing a reliable record of early human adaptation. Over time, hominin populations migrate out of Africa into Asia and Europe. Fossil discoveries and genetic data, including mitochondrial DNA analysis, trace these dispersals. Populations adapt to diverse climates, developing regional variations in physiology and behavior. Evidence from skeletal morphology, isotopic analysis, and paleoenvironments shows that humans respond predictably to environmental pressures, with adaptations in body size, limb proportions, and metabolic processes reflecting local ecological conditions. Around 300,000 years ago, anatomically modern humans, Homo sapiens, emerge in Africa. Fossils show a cranial capacity averaging 1,350 cubic centimeters, with reduced brow ridges, rounded skulls, and a prominent chin. These physical characteristics distinguish Homo sapiens from other hominins. Genetic sequencing confirms the species' origin in Africa and subsequent expansion, providing measurable evidence for population migration patterns and interbreeding with other hominins such as Neanderthals and Denisovans. Early Homo sapiens develop increasingly complex tools and cultural practices. Stone blades, bone implements, and hafted tools reflect an understanding of material properties and mechanical advantage. Archaeological sites preserve these artifacts, along with evidence of pigment use, symbolic markings, and personal ornaments. These objects indicate cognitive development, abstract thinking, and social organization. Observational analysis allows reconstruction of behavior and skills, confirming that early humans possessed advanced problem-solving abilities and planning capacity. Social structures evolve alongside cognitive development. Humans form cooperative groups for hunting, foraging, and protection. Ethnographic comparison with contemporary hunter-gatherer societies provides insight into early social dynamics, division of labor, and resource sharing. Anthropologists observe patterns of group size, kinship, and cooperative behavior that are consistent across environments, suggesting predictable advantages to social cooperation in human survival. Language likely develops gradually during this period. While direct evidence is limited, anatomical adaptations such as the position of the hyoid bone, neural complexity, and genetic markers such as FOXP2 indicate increasing communicative ability. Linguistic capability allows the transfer of knowledge, coordination in hunting and gathering, and the preservation of cultural practices. These evolutionary changes are measurable through anatomical studies, genetic analysis, and behavioral inference, reinforcing a scientific understanding of early human cognition. Homo sapiens expand geographically, encountering and interacting with other hominins. Fossil evidence shows coexistence with Neanderthals in Europe and Denisovans in Asia. Genetic analysis reveals interbreeding events, leaving traces in the genomes of contemporary humans. Observational and molecular evidence demonstrates that early human populations were not isolated but dynamic, exchanging genes and knowledge, which influenced adaptability and survival across different ecosystems. Agricultural experimentation begins around 12,000 years ago in multiple regions. Archaeological remains of cultivated plants, storage facilities, and domesticated animals indicate a transition from purely foraging to controlled food production. This shift allows population growth, settlement, and environmental modification. Radiocarbon dating, pollen analysis, and soil chemistry provide precise evidence for the timing and scale of these changes, showing that humans increasingly influence their surroundings through systematic observation and experimentation. Humans continue to innovate, developing tools, clothing, shelter, and social structures suited to diverse environments. Evidence of early art, music, and ritual practices appears in caves, carved objects, and burial sites. These behaviors indicate symbolic thought, cultural transmission, and long-term planning. Anthropologists study these artifacts through stratigraphy, isotopic dating, and comparative analysis, confirming that humans possess unique cognitive capacities that influence both individual and group survival. You notice that throughout this period, human expansion and adaptation are measurable and evidence-based. Fossil morphology, genetics, tool technology, and environmental reconstructions provide consistent data. Evolutionary processes, such as natural selection, gene flow, and cultural adaptation, operate predictably, producing both physical and behavioral diversity. Every migration, technological advancement, and cultural practice can be linked to environmental pressures and measurable outcomes, illustrating the gradual accumulation of knowledge and capability in early human populations. Reflecting on this emergence, you perceive humanity as the product of incremental change over millions of years, guided by evolutionary principles, environmental interaction, and cognitive development. Each step, anatomical, technological, and social, is supported by observable evidence. Humans are simultaneously a biological species and a cultural one, capable of modifying their environment, recording their history, and learning from experience. This understanding frames humanity's presence within the broader, evidence-based timeline of life on Earth. The progression from early hominins to Homo sapiens demonstrates the predictable operation of natural selection, genetic variation, and environmental adaptation. Fossil remains, archaeological artifacts, and genetic studies confirm each stage, allowing you to follow humanity's journey without speculation. You notice that every adaptation, from tool use to language, arises from measurable interactions with the environment, providing a clear, scientific view of human emergence and laying the foundation for the future exploration of culture, observation, and technology. You begin by observing the sky as early humans would have, noticing the sun rising and setting, the phases of the moon, and the constellations shifting with the seasons. These patterns are consistent, predictable, and measurable, forming the foundation of early astronomical understanding. Across many regions, humans recognize repetitive cycles and begin to organize time according to observable celestial motions. The reliability of these cycles allows early communities to schedule planting, harvesting, and migration with increasing precision. Stone arrangements and ancient structures provide the earliest evidence of systematic sky observation. Sites such as Göbekli Tepe, Nabta Playa, and later Stonehenge exhibit alignments with solstices, equinoxes, or prominent stars. Archaeologists measure the orientation, construction patterns, and dating of these structures to confirm intentional astronomical alignment. These findings indicate that humans were capable of recording and predicting celestial events, using observation to guide both practical and ceremonial life. Early humans also monitor lunar cycles. The moon's phases repeat predictably every 29.5 days, influencing tides, nocturnal illumination, and ritual calendars. Counting and recording lunar cycles allows the development of early timekeeping systems, visible in carved bones, notched sticks, and pottery marks. These artifacts provide measurable evidence of intentional observation, demonstrating that humans could quantify and track astronomical cycles without modern instruments. Solar tracking forms another critical dimension of early astronomy. Observing the sun's rising and setting points over the year reveals the solar year's duration. People note the solstices and equinoxes, using shadows, posts, or markers to track seasonal changes. Measurement of sunlight angles and day length allows the establishment of rudimentary calendars, supporting agricultural planning. These practices are documented by both physical structures and written records, confirming that early humans developed precise observational skills to monitor celestial motion. The stars themselves become reference points. Constellations act as mnemonic systems, helping people track the passage of time and navigate landscapes at night. Groups of bright stars, particularly those near the celestial poles or along the ecliptic, provide stable markers. Early navigators exploit these fixed positions, and cultural traditions preserve knowledge across generations. Observational astronomy is therefore grounded in careful attention, repeated measurement, and systematic record-keeping, all verifiable through archaeoastronomical studies. Humanity's earliest calculations of lunar and solar cycles form the basis for calendars. Civilizations such as the Babylonians, Egyptians, and Mayans create systems that align months with lunar phases and years with solar motion. These calendars are designed through observation and computation, incorporating intercalary periods to correct for the slight mismatch between cycles. The predictability of celestial motion allows such calculations to be accurate over centuries, demonstrating the capacity for evidence-based reasoning in early astronomy. Early mathematical concepts emerge from the need to quantify and predict celestial events. Counting days, dividing circles for angles, and measuring shadow lengths represent practical applications of arithmetic and geometry. For example, the Egyptians used gnomons to measure solar elevation, deriving accurate seasonal calendars. These techniques rely on observation and physical measurement, not speculation, providing reproducible results that connect human cognition to empirical reality. You notice that early astronomers also identify planetary motion. Mercury, Venus, Mars, Jupiter, and Saturn move differently from stars, wandering against the background constellations. Careful tracking over months and years allows early cultures to predict conjunctions and retrograde motion. Recorded observations, preserved in cuneiform tablets and inscriptions, demonstrate systematic monitoring and pattern recognition, establishing the foundation for predictive astronomy and eventually mathematical modeling of planetary motion. Cultural practices and ritual calendars reflect astronomical understanding. Agricultural societies time planting and harvesting by observing heliacal risings of bright stars. Lunar calendars guide ritual ceremonies, ensuring consistency across generations. Archaeological evidence, including aligned temples and documented festivals, confirms that humans integrate astronomy into social organization and daily life. The connection between observation, measurement, and practical application demonstrates that early astronomy is an evidence-driven activity, grounded in repeated, predictable patterns. The systematic observation of celestial cycles also contributes to navigation. Polynesian voyagers, for example, use star positions, the moon, and the sun to traverse vast ocean distances. Observational techniques include noting rising and setting points, star paths, and seasonal shifts. These methods are verifiable and reproducible, illustrating that accurate, empirical understanding of the sky allowed humans to expand across continents and oceans. Navigation based on celestial observation is therefore a direct extension of evidence-based astronomy, connecting perception to practical problem-solving. You recognize that early humans combine observation with memory, oral tradition, and physical markers to create a coherent understanding of the cosmos. Patterns in the sky are predictable, and humans develop techniques to quantify, track, and anticipate celestial events. Archaeological and ethnographic evidence confirms that these methods are effective, allowing societies to regulate agriculture, migration, and ritual life with precision. The systematic nature of early astronomy demonstrates the human ability to comprehend complex natural cycles through careful attention and measurement. Reflecting on these developments, you see that humanity's earliest scientific activity is rooted in observation, repetition, and verification. Sun, moon, and stars are not merely distant objects but tools for measurement and understanding. These methods establish a foundation for mathematics, record-keeping, and future scientific inquiry. The sky becomes both a calendar and a laboratory, demonstrating that careful observation and reasoning can reveal patterns and laws that extend far beyond immediate human experience. The consistent and predictable motions of celestial objects provide the framework for a growing understanding of the universe. The accuracy of early human astronomy foreshadows the systematic observations that will later lead to telescopes, planetary measurements, and space exploration, where human ingenuity continues to follow patterns established by the regularity of the cosmos. You begin by observing the development of telescopes, which extend human vision far beyond the naked eye. In the early 17th century, Galileo Galilei uses a refracting telescope to study the moon, Jupiter's moons, and the phases of Venus. Observations of surface features and orbital motion provide empirical evidence that the Earth is not the center of the universe, confirming the heliocentric model first proposed by Copernicus. The precision of these measurements demonstrates how extending perception allows direct testing of hypotheses against observable data. Modern optical telescopes improve in size, resolution, and sensitivity, enabling the observation of distant stars and galaxies. Spectroscopy allows the measurement of composition, temperature, and velocity. Absorption lines and Doppler shifts provide precise information about stellar elements and motions. By analyzing spectra, astronomers determine redshifts, confirming that most galaxies are receding, a measurable observation supporting the expansion of the universe. You notice that each step, from instrument design to data interpretation, is methodical and grounded in repeatable evidence. Radio astronomy emerges in the 20th century, opening an additional window into the cosmos. Radio telescopes detect emissions from hydrogen clouds, pulsars, and distant galaxies. These observations reveal structures and phenomena invisible in optical wavelengths. Precise timing measurements from pulsars allow tests of general relativity, confirming predictions about time dilation and gravitational waves. Each finding is independently verifiable, demonstrating the reliability of observational techniques across different portions of the electromagnetic spectrum. Space-based telescopes further eliminate atmospheric interference, providing unparalleled clarity. The Hubble Space Telescope captures images of distant galaxies, nebulae, and star clusters with extraordinary resolution. Observations of Cepheid variable stars enable accurate distance measurements, calibrating the cosmic distance ladder. The light from these objects, measured and recorded over decades, provides a consistent and reproducible record of the universe's structure, expansion rate, and history. Hubble's data confirm patterns predicted by theory, demonstrating the alignment of observation and mathematical modeling. Humanity's exploration extends beyond observation into direct investigation. Space probes and robotic missions visit planets, moons, asteroids, and comets, returning high-resolution imagery, surface composition data, and atmospheric analysis. The Voyager spacecraft, launched in 1977, provide measurements of planetary magnetospheres, solar wind, and outer solar system conditions. These observations confirm theoretical models of planetary formation and dynamics, illustrating that empirical exploration extends the reach of scientific understanding. The study of exoplanets has become a central focus of modern astronomy. Missions such as Kepler and TESS identify thousands of planets orbiting other stars. Transit photometry measures periodic dips in stellar brightness, while radial velocity observations detect gravitational effects on host stars. Each discovery is confirmed through repeatable, independent observation, providing measurable evidence of planetary systems beyond our own. These findings demonstrate that planetary formation is a universal process governed by predictable physical laws. Cosmology, grounded in observation and theory, reveals the large-scale structure of the universe. Galaxy surveys, cosmic microwave background measurements, and gravitational lensing data provide precise evidence of matter distribution, dark energy, and dark matter effects. Instruments such as the Planck satellite map temperature fluctuations in the cosmic microwave background, confirming models of early universe evolution. You perceive that each measurement builds upon previous data, forming a cohesive and testable framework for understanding cosmic history. Human missions to the Moon and robotic exploration of Mars illustrate the application of physics and engineering in practical space exploration. Lunar landings provide direct geological samples, confirming theories about the Moon's formation through isotopic analysis and radiometric dating. Mars rovers, such as Curiosity and Perseverance, analyze soil chemistry, search for evidence of past water, and monitor atmospheric conditions. Each dataset is meticulously calibrated, recorded, and interpreted, demonstrating the precision and reliability of space-based experimentation. Observations of high-energy phenomena, such as supernovae, black holes, and neutron stars, expand understanding of extreme physical processes. X-ray and gamma-ray telescopes detect emissions from energetic sources, allowing measurement of temperatures, luminosities, and particle acceleration. Observed gravitational wave events, confirmed by detectors like LIGO and Virgo, provide independent verification of Einstein's predictions. These discoveries illustrate the capacity of technology to extend human perception into regimes otherwise inaccessible, translating indirect measurements into accurate, verifiable knowledge about the cosmos. The discovery and classification of galaxies, from spirals to ellipticals and irregulars, depend on systematic observation and measurement. Redshift surveys confirm that most galaxies are moving away from one another, providing direct evidence of the expanding universe. Morphological classification and spectral analysis allow astronomers to reconstruct star formation histories, mass distribution, and chemical evolution. Observational consistency across independent instruments and surveys ensures reliability, confirming that human understanding is firmly rooted in reproducible data. Astrometry, the precise measurement of positions and motions of stars, informs navigation, distance determination, and dynamic modeling. Gaia, a space observatory, provides high-precision parallax measurements for over 1 billion stars, allowing the construction of a detailed three-dimensional map of the Milky Way. These measurements are accurate to microarcseconds, providing an unprecedented view of stellar motion, cluster dynamics, and galactic structure. You notice that precision and repeatability form the basis of knowledge, enabling conclusions that are both measurable and verifiable. Collaboration across disciplines enhances observational reliability. Data from ground-based telescopes, space missions, and theoretical simulations converge to provide a consistent picture of cosmic phenomena. Independent replication, peer review, and standardized calibration ensure that findings are trustworthy. Each step, from photon detection to data interpretation, is grounded in measurable physical processes, reinforcing the evidence-based nature of modern astronomy. You recognize that the cumulative effect of centuries of observation, measurement, and technological advancement has transformed humanity's understanding of the universe. Patterns, laws, and structures emerge clearly from repeated, verifiable observation, and every discovery is confirmed through careful analysis. Space exploration and astronomy illustrate the capacity of humans to extend perception, interpret complex data, and construct coherent, evidence-supported models of the cosmos. Reflecting on this progress, you perceive that the universe is both vast and comprehensible through methodical observation. Telescopes, spacecraft, and detectors reveal galaxies, exoplanets, and cosmic phenomena with measurable precision. Human ingenuity, guided by empirical evidence and physical law, continues to expand the range of observation, connecting Earth-based understanding with the broader universe and preparing the mind to contemplate time, space, and cosmic history. You begin by observing light as it travels across space. Each photon carries information from the moment of its emission, allowing you to see events that occurred millions or even billions of years ago. The finite speed of light, precisely 299,792 kilometers per second, creates a natural record of cosmic history. Observing a galaxy a billion light-years away means looking back a billion years in time. This principle allows astronomers to reconstruct the timeline of the universe from a direct, measurable source. Redshift measurements provide a method for quantifying cosmic expansion. Light from distant galaxies shifts toward longer wavelengths due to the stretching of space. By measuring the amount of redshift, astronomers determine the rate at which a galaxy is receding, providing a basis for estimating distances and the age of cosmic structures. Hubble's law, confirmed through numerous independent observations, relates redshift to distance, allowing precise calculation of the universe's expansion rate and its temporal framework. The cosmic microwave background radiation serves as a snapshot of the universe approximately 380,000 years after the Big Bang. This relic radiation is measured with high precision by satellites such as COBE, WMAP, and Planck. Temperature fluctuations, on the order of microkelvins, provide detailed information about early density variations that would later evolve into galaxies and clusters. By analyzing these fluctuations, scientists accurately infer the age of the universe at roughly 13.8 billion years, establishing a chronological anchor for cosmic events. Light travel time also influences the observation of stars within our galaxy. When you observe the Sun, you are seeing it as it was about 8 minutes ago. Observing Alpha Centauri, the nearest stellar system, means seeing it as it appeared 4 years ago. These measurable delays illustrate the continuous relationship between space and time, demonstrating that every observation inherently involves a temporal component. Light acts as a natural chronometer, preserving a record of events and allowing verification of models through observation. Radiometric dating provides a complementary method for measuring time on Earth and within the solar system. Isotopes such as uranium-238 decay into lead-206 at known rates, allowing precise determination of rock and meteorite ages. Radiometric evidence confirms that Earth formed approximately 4.54 billion years ago, and that the oldest known minerals date to over 4.4 billion years. Each measurement is reproducible, calibrated against decay constants, and cross-verified using multiple isotopic systems, establishing a reliable timeline for geological and planetary history. Stellar life cycles also serve as indicators of cosmic time. Nuclear fusion processes within stars operate at rates determined by mass, composition, and physical laws. Observing stellar populations in clusters allows measurement of age through main sequence turn-off points. Theoretical models, supported by observations of clusters such as M67 and globular clusters, demonstrate predictable patterns in stellar evolution. Stars, in their predictable progression from formation to death, provide measurable milestones for understanding temporal sequences on a cosmic scale. You notice that general relativity further refines the concept of cosmic time. Massive objects warp spacetime, affecting the passage of time for nearby observers. Observations of gravitational lensing, time dilation in pulsars, and orbiting satellites confirm these effects. Experiments such as the Haffel-Keating experiment with atomic clocks on airplanes verify that velocity and gravitational potential influence elapsed time. Time, therefore, is not absolute but measurable relative to the observer, consistent with predictions of Einstein's equations. In addition to relativistic effects, the motion of Earth introduces periodic variations in temporal measurement. Observations of celestial objects must account for orbital motion, rotation, and precession. Techniques such as barocentric correction and standard reference frames allow astronomers to remove local time distortions, ensuring that measured events reflect true cosmic intervals. These procedures, verified through repeated observation, enable consistent comparison of events across space and time. Supernovae, particularly type Ia, provide another temporal measure. Their luminosity follows predictable patterns, enabling them to serve as standard candles. By comparing observed brightness to intrinsic luminosity, astronomers determine distances with high precision. Combined with redshift data, these observations allow reconstruction of the universe's expansion history. Measurements consistently indicate that the expansion rate has accelerated in recent cosmological epochs, a conclusion supported by multiple independent datasets and methods. Observations of binary pulsars offer measurable evidence of time evolution in extreme conditions. Pulsars emit periodic radio pulses with extraordinary regularity. By timing these pulses, astronomers detect minute variations caused by orbital motion, gravitational waves, and relativistic effects. These observations confirm theoretical predictions of general relativity and allow precise measurement of orbital decay, demonstrating that time can be quantified under both ordinary and extreme cosmic conditions. Cosmological simulations provide a dynamic perspective on cosmic time. Using measured physical laws, astronomers model the formation of large-scale structures, galaxy clusters, and cosmic filaments. Observational evidence from surveys such as SDSS and DES validates the simulations, confirming that the passage of cosmic time shapes structures in predictable ways. Simulated timelines, constrained by redshift, cosmic microwave background data, and nucleosynthesis calculations, demonstrate the continuity and measurability of cosmic evolution. Time in the universe also connects with nucleosynthesis in the first few minutes after the Big Bang. Observations of primordial element abundances, including hydrogen, helium, and lithium, are consistent with theoretical predictions from Big Bang nucleosynthesis. Measured ratios in stars, gas clouds, and the cosmic microwave background allow verification of the early universe's timeline. These results reinforce that cosmic events follow measurable physical laws, and that time itself can be traced through the evolution of matter. You recognize that combining light travel time, redshift, radiometric dating, stellar life cycles, relativistic corrections, and nuclear synthesis allows a coherent, evidence-based framework for cosmic time. Each method is independently verifiable, yet all converge to a consistent understanding of the universe's age and history. Time, though complex and relative, is measurable and predictable, providing a structure that allows you to situate cosmic events within a precise temporal order. Reflecting on this, you perceive time as both observable and calculable. The universe retains a record in light, matter, and radiation, each carrying measurable temporal information. Observational techniques, grounded in physics and repeatable measurements, allow reconstruction of the sequence of cosmic events from the Big Bang to the present. Time becomes a tool for understanding cosmic evolution, bridging vast distances and ages, and preparing the mind to appreciate both the immensity and the structure of the universe. You begin by observing Carl Sagan's approach to astronomy and science communication. Sagan emphasizes clarity, systematic explanation, and empirical evidence. His work demonstrates that complex astronomical concepts, from the vastness of the universe to the processes of planetary formation, can be conveyed accurately to the public. He relies on observational data, verified measurements, and peer-reviewed research, using accessible language without compromising scientific integrity. Sagan develops the cosmic calendar as a tool to visualize the history of the universe. In this representation, the 13.8 billion-year lifespan of the universe is compressed into a single calendar year. Each month, day, and second corresponds to measurable spans of time. Galaxies, stars, and planets are placed in precise temporal order based on astrophysical observations and cosmological models. This framework allows you to comprehend the timing of events such as the formation of the Milky Way, the Sun, and Earth in a measurable and factual way. His emphasis on observational evidence is apparent throughout his work. Sagan references stellar nucleosynthesis, which explains the formation of elements within stars, and the accumulation of these elements in planets and life forms. He cites spectroscopic data, radiometric dating, and space mission findings to support every assertion. By focusing on reproducible measurements and verified theory, Sagan models a way of understanding the universe that is both accurate and intellectually engaging. You notice that Sagan also highlights the scale of human history in comparison to cosmic time. On the cosmic calendar, the emergence of Homo sapiens occurs in the last few seconds of December 31st. Recorded civilization appears within the final fractions of a second. These comparisons, grounded in evidence from archaeology, geology, and cosmology, provide perspective without exaggeration, reinforcing the briefness of human presence relative to the universe's age while remaining firmly factual. Planetary exploration features prominently in Sagan's work. He communicates findings from missions such as Mariner, Viking, Voyager, and Pioneer. Measurements of atmospheric composition, surface features, magnetic fields, and radiation environments are presented systematically. Observations of Venus, Mars, and the outer planets are explained using data collected by spacecraft instruments, ensuring that conclusions rest on empirical evidence. Sagan emphasizes the reproducibility of observations, noting that independent teams confirm findings before they are widely accepted. Sagan's advocacy for the search for extraterrestrial intelligence, including the SETI program, is grounded in measurable criteria. He considers the properties of radio waves, the likelihood of habitable zones around stars, and planetary system formation as derived from observation and astrophysical models. The possibility of detecting signals is framed in terms of probability and physical feasibility, rather than speculation. Calculations of signal strength, distance, and frequency are based on measurable physics, illustrating Sagan's commitment to evidence-based reasoning. Education and public engagement are central to Sagan's vision. His television series and books convey complex concepts such as the electromagnetic spectrum, gravity, planetary atmospheres, and cosmic evolution with precise definitions. When he explains nuclear fusion in stars or the expansion of the universe, he references observational data and well-established physical laws. Demonstrations, examples, and historical context support understanding, allowing accurate comprehension without oversimplification or fantasy. Sagan also emphasizes the interconnectedness of observation and theory. He illustrates how measurements, such as stellar parallax, redshift, and radiometric dating, combine with theoretical models to produce reliable conclusions. The interplay of data and mathematical description exemplifies the scientific method in practice. Observations are interpreted within frameworks grounded in physics and cosmology, ensuring that conclusions are testable and verifiable. You notice that Sagan consistently addresses uncertainty and the limits of current knowledge. He explains that while many measurements are precise, open questions remain in areas such as planetary formation, interstellar chemistry, and the search for life beyond Earth. By acknowledging these limits, Sagan models scientific integrity, showing that curiosity, observation, and skepticism coexist in the process of discovery. This perspective allows understanding without exaggeration or unfounded speculation. Sagan's communication style balances awe with factual accuracy. He conveys the scale of the universe, the abundance of stars and galaxies, and the potential for life elsewhere, while always grounding statements in observational evidence. For example, when discussing the frequency of potentially habitable planets, he references exoplanet surveys and statistical analysis. When describing cosmic evolution, he cites radiometric dating and measurements of cosmic background radiation. Each claim is tied to measurable data, reinforcing credibility. Through Sagan's work, you see the power of visualization in science education. Graphs, timelines, and the cosmic calendar transform abstract numbers into comprehensible scales. These tools allow you to follow the progression of the universe, from the formation of the first atoms to the emergence of stars, planets, and life, using empirical evidence rather than metaphor. The effectiveness of these visualizations is measurable, demonstrated by the widespread adoption of the cosmic calendar in educational contexts. You also notice that Sagan highlights the importance of cumulative knowledge. Observations across decades and centuries are combined to form a coherent understanding of planetary systems, stellar evolution, and galactic structure. Each generation of astronomers builds on prior measurements, using better instruments and refined techniques. This incremental approach demonstrates that scientific understanding grows through systematic observation, verification, and reinterpretation of data, creating a dependable framework for knowledge. Reflecting on Sagan's contributions, you perceive that his vision combines clarity, rigor, and curiosity. Scientific inquiry, evidence-based reasoning, and careful measurement are central to understanding the universe. Observation, supported by mathematical modeling, permits accurate reconstruction of cosmic events and timelines. By presenting this knowledge accessibly, Sagan enables the mind to grasp the enormity of time, the processes of the universe, and humanity's brief but measurable presence within it. The evidence-based clarity in Sagan's work leaves you considering how human understanding of the cosmos relies on systematic observation, reproducible data, and careful interpretation. Every measurement, from stellar spectra to planetary imaging, connects to the larger framework of knowledge, demonstrating that curiosity and rigor together allow the mind to explore the universe accurately and comprehensively. You begin by visualizing the cosmic calendar, where 13.8 billion years of universal history are compressed into a single year. Each month represents over 1 billion years, each day spans approximately 40 million years, and each second corresponds to roughly 440 years. In this framework, the Earth forms around early September, oceans appear in early September, and life emerges in late September. Multicellular organisms appear in mid-December, with dinosaurs emerging in the final days of December, and their extinction occurring just hours before midnight on December 31st. Homo sapiens appear only in the last few seconds of the year. Fossil evidence and genetic data place anatomically modern humans in Africa around 300,000 years ago. Tools, fire use, and migration patterns are documented and dated through archaeology, providing measurable evidence of early human activity. The brevity of our species' existence relative to cosmic time is apparent when you map these events onto the calendar. All of recorded civilization, agriculture, and urban development occupy less than a single minute before midnight. You trace the rise of agriculture through radiocarbon dating of plant and animal remains. By around 12,000 years ago, humans begin cultivating grains, domesticating animals, and forming settlements. These measurable activities appear within the final fractions of a second on the cosmic calendar, emphasizing the rapid pace of technological and societal change in contrast to the slow evolution of stars, planets, and ecosystems. Archaeological evidence provides precise temporal markers, allowing accurate placement of these milestones on the calendar. Cities develop, and early civilizations emerge within the last few seconds of the year. Mesopotamia, Egypt, the Indus Valley, and China establish organized societies, writing systems, and governance structures. Artifacts, written records, and carbon-dated architectural remains confirm the timing and scale of these developments. Each measurable piece of evidence contributes to a precise chronology, situating human activity within the broader context of planetary and cosmic evolution. Written history appears even closer to the calendar's final second. The invention of writing, beginning around 5,000 years ago, allows humans to record events, track astronomical phenomena, and preserve knowledge systematically. Archaeological finds such as cuneiform tablets, hieroglyphs, and inscriptions provide datable evidence. These records are precise, measurable, and repeatable sources of information, establishing a verifiable timeline for intellectual, cultural, and technological developments. Technological advancement accelerates rapidly in the final moments of the cosmic calendar. Industrialization, mechanization, and scientific discovery occur within microseconds on this scale. The evidence is found in dated patents, industrial records, and preserved instruments. Scientific achievements, from understanding electromagnetism to the development of quantum mechanics and relativity, are documented and reproducible. Each step is measurable, reinforcing that even the fastest periods of human activity can be traced systematically through observable data. You consider the expansion of human populations across continents. Genetic studies and fossil evidence provide measurable timelines of migration out of Africa and the peopling of Europe, Asia, the Americas, and Oceania. Archaeologists verify the timing of these migrations through radiocarbon dating of tools, habitation sites, and human remains. These movements, mapped onto the cosmic calendar, occupy mere seconds, yet they shape the distribution and diversity of contemporary human populations in a measurable, evidence-based way. Cultural and scientific achievements appear in the final instance. Written literature, mathematics, philosophy, and astronomy develop in measurable sequence. Astronomical records, such as Babylonian observations and Chinese eclipse documentation, align with physical evidence and computational models. Each observation is dated, reproducible, and verifiable, demonstrating that human intellectual activity, though brief in cosmic time, is deeply rooted in empirical measurement and careful record-keeping. You notice that despite this brevity, humans influence planetary systems measurably. Climate change, deforestation, and the redistribution of species are documented through geological, ice core, and sedimentary evidence. Carbon isotope ratios, temperature proxies, and deforestation markers indicate significant changes in Earth systems within the last few hundred years, equivalent to fractions of a second on the cosmic calendar. These measurable alterations underscore the capacity of humans to act on a planetary scale within an extremely brief temporal interval. Exploration of space extends humanity's measurable influence beyond Earth. Spacecraft, satellites, and observatories provide a record of human activity in space. Each launch, measurement, and observation is precisely timed and recorded, contributing to a documented expansion into the solar system. These events, placed within the final instance of the cosmic calendar, illustrate the remarkable concentration of human innovation in the most recent moments of cosmic history. Scientific methodology underlies all placement on the calendar. Radiometric dating, dendrochronology, ice cores, genetic sequencing, and historical records provide independent verification of timelines. Each method is reproducible and cross-validated, creating a robust framework for situating humanity within cosmic history. By combining multiple lines of evidence, you can accurately map the brief emergence and activities of humans alongside the vast, measurable progression of stars, galaxies, and planetary evolution. You reflect on the perspective provided by the cosmic calendar. Humanity occupies an almost imperceptible fraction of time, yet this brief interval contains extraordinary cognitive, cultural, and technological development. Every archaeological site, artifact, and written record contributes to a precise understanding of temporal placement. The accumulation of evidence across disciplines confirms that humans are a recent addition to a universe measured in billions of years, emphasizing the continuity and scale of cosmic processes. This measurable brevity encourages reflection on the relationship between earthly history and cosmic evolution. Observations of the Milky Way, solar system, and distant galaxies provide context for human emergence, demonstrating that planetary and stellar evolution set the stage for life. Each scientific measurement, from star formation to radiometric dating, reinforces that human history, though brief, is traceable, verifiable, and situated within a vast and predictable framework of cosmic events. As you consider the full span of the cosmic calendar, the evidence underscores that the timing, sequence, and impact of human activity are both precise and measurable. Fossils, artifacts, genetic data, and historical records converge to situate humanity within an immense, well-documented timeline. The brief interval of human history contrasts with the extended processes of the universe, providing both perspective and clarity. You perceive that even within such a short fraction of time, humans achieve measurable change, record knowledge, and expand understanding through observation and reasoning. Each discovery, technological advancement, and societal development is grounded in evidence, confirming that the human presence, though brief, is embedded in a comprehensible temporal framework. The cosmic calendar illustrates that systematic observation allows the mind to relate daily existence to the scale of cosmic time. You begin by considering the continuous expansion of the universe. Observations of distant galaxies show that space itself stretches over time, causing galaxies to recede from one another. This expansion is measurable through redshift, calibrated using standard candles and spectral analysis. The rate, expressed as the Hubble constant, is determined with increasing precision through multiple independent methods, including observations from the Hubble Space Telescope, supernova surveys, and cosmic microwave background measurements. The universe grows larger, and each measurement confirms a predictable trend in cosmic evolution. Galaxy formation continues across cosmic time. Matter collapses under gravity, forming stars, star clusters, and galaxies that interact in measurable ways. Collisions between galaxies are observed through telescopes and mapped using spectroscopic data, showing changes in structure, star formation rates, and motion. Simulations based on physical laws reproduce these interactions accurately, confirming that galaxy evolution is governed by gravitational dynamics, stellar physics, and observable chemical processes. You notice that even in the vastness of space, measurable processes unfold consistently. Star formation persists in nebulae across the universe. Gas clouds collapse, igniting nuclear fusion when density and temperature reach precise thresholds. Observatories such as ALMA and the James Webb Space Telescope detect these regions, measuring radiation, chemical composition, and mass. By observing young stellar objects and protoplanetary disks, astronomers determine the timescales of star and planet formation. These measurements are consistent with models derived from physics, confirming that stellar processes are both predictable and ongoing. Planetary systems continue to form around new stars. Exoplanet detection relies on transit photometry, radial velocity, and direct imaging. Each method provides measurable parameters: orbital period, distance from the star, mass, and composition. Analysis of these systems demonstrates the universality of planetary formation and the diversity of possible configurations. Data from thousands of exoplanets confirm that planetary formation is a common, predictable process, illustrating that the creation of worlds is an ongoing and measurable cosmic activity. You notice that cosmic phenomena occur on multiple timescales. Supernovae mark the death of massive stars, recycling elements into the interstellar medium. The remnants expand at measurable velocities, enriching the surrounding space with heavy elements. Observations of these events provide precise data on energy output, composition, and distance. Neutron stars and black holes form in predictable ways following gravitational collapse, and their properties can be measured using X-ray, gamma-ray, and gravitational wave observatories. Each process follows physical laws and generates verifiable evidence. Black holes remain objects of active observation. Gravitational wave detection confirms collisions of massive black holes, providing measurable data on mass, spin, and energy release. Imaging of black hole shadows, as achieved by the Event Horizon Telescope, reveals the structure of event horizons and surrounding accretion disks. The data are consistent with predictions from general relativity, demonstrating that even the most extreme regions of space behave according to observable, measurable physical principles. Cosmic expansion and evolution also include dark matter and dark energy. Observations of galaxy rotation curves, gravitational lensing, and large-scale structure provide measurable evidence for dark matter's gravitational influence. Dark energy, inferred from supernova luminosity distance measurements, drives the accelerated expansion of the universe. While these components are not directly observable, their presence is measured and quantified through repeated, independent observations, showing that even unseen forces are constrained by empirical evidence. The ongoing processes in the universe continue to produce measurable signals. Light from distant quasars, gamma-ray bursts, and pulsars provides data about extreme environments. Observations are recorded, cataloged, and analyzed to refine models of physical behavior. By combining data from multiple wavelengths and instruments, astronomers verify predictions about energy output, composition, and dynamics. These measurements allow continuous refinement of understanding, ensuring that knowledge remains anchored in observation rather than speculation. Human understanding of the universe progresses alongside these cosmic processes. Telescopes, probes, and detectors extend perception, revealing phenomena from nearby planets to the edge of observable space. Advances in computing and simulation allow models to match observational data with high precision. Theoretical frameworks, constrained by measurement and repeatable observation, predict behaviors that are subsequently verified. Each new observation contributes to a continuously updated, evidence-based picture of the cosmos. You notice that unanswered questions remain, each measurable and approachable through systematic study. The nature of dark matter and dark energy, the formation of supermassive black holes, and the potential habitability of exoplanets are all areas where ongoing observation and experimentation generate data. Future telescopes, Gravitational wave detectors and planetary missions will provide measurable insights, allowing theories to be tested, refined, or revised based on repeatable evidence. The pursuit of these answers is both methodical and patient. Cosmic time continues, and light from increasingly distant regions reaches observation instruments. You consider that each photon represents a measurable record of past events. Observing these signals allows reconstruction of galaxy formation, star birth, and chemical evolution over billions of years. The universe maintains its record, and human technology enables precise measurement and interpretation. Each observation contributes to a cumulative, verifiable understanding of ongoing cosmic evolution. Reflecting on all of this, you perceive that the universe is immense, dynamic, and comprehensible through careful observation. Patterns, processes, and interactions occur consistently and measurably. Human curiosity, supported by technology and guided by empirical reasoning, allows comprehension of these processes without speculation. You see that the vast scales of space and time can be understood through patient measurement, observation, and analysis. Even as questions remain and exploration continues, the structure of knowledge provides reassurance. Measurable laws govern motion, energy, and matter. Telescopes, probes, and detectors extend perception, while systematic observation ensures that understanding remains anchored in reality. The universe unfolds continuously, offering evidence, patterns, and predictable behavior for those who follow observation with rigor and patience. You feel the gentle expanses of space extending beyond current observation. Galaxies form, stars ignite and die, and planets emerge, all in accordance with measurable laws. Human observation, precise and systematic, continues to uncover these processes, connecting each measurement to a larger, coherent understanding. The ongoing universe, vast yet understandable, invites calm reflection and measured curiosity, allowing the mind to rest while remaining attentive to the continuity of cosmic time and the evidence it presents.